So the last question of this problem, show that the sum of non-convex functions can be convex for any alpha bigger than or equal to 0. And as a bonus, we try to make it alpha strongly convex. So to work in simple land, because we're lazy, let's work in 1D. So when D equals 1, D, remember, D is the dimension of the vectors we defined, right? So here we define W prime and RD. So now we're working in one dimension is what we're saying. What does convexity mean in one dimension? So F convex, if and only if, and this also means this, so this goes both ways. The second derivative of x is bigger than or equal to 0 for all x. Now there's a caveat here, which we have to say f is convex. This definition works for when we're talking about a specific interval. So f is convex in an interval if and only if f prime prime of x is bigger than or equal to 0 for all x in that interval. Okay, and let's define alpha convexity, alpha strongly convexity in D1 as well. So when D is equal to 1, well, we can just, since we're lazy, we can do this. So what's going to change in this definition is this 0 is going to be alpha. Okay, here's the change, right? So F is alpha strongly convex. Let me write it. In an interval, if and only if the following hold, right? So great, we have our definitions now. What do we do? So now we will just try to find two functions in a sort of a smart way, right? And then we'll add them up like we've been doing for the other exercises. So let's define two functions. Let f of x equal xq, and g of x is equal to alpha x squared minus xq. Now, what did we do here? Here, if you notice, we have these two functions which we've defined, which we want to be non-convex, right? And notice that we, like in the second function we defined the first functions. So here, what we're planning to do in the future is, because we have to show the sum of these non-convex functions is convex, look, when we're going to add these two guys up, these are going to cancel. And these are the non-convexity part of the function, right? So we can rewrite this, if you will, as, maybe this is clearer, minus f of x, right? And so in the future, we plan to remove this. This is our like plan in the future. Right now, we have to show that these guys are not convex, right? So we're in one dimension, so we can just take the second derivative of each. F prime prime of x is equal to 6x, right? Which is smaller than 0 for x smaller than 0, hence non-convex on R. Non-convex when x is smaller than 0. What did I write here? It's hard to talk and write at the same time. Sometimes you hallucinate. And g prime prime, what is g prime prime? So the second derivative of g is 2 alpha, 2 alpha minus 6x, right? Which is smaller than 0 for Let's do a bit of no. This goes here. For x bigger than 2 over 6 alpha, which is alpha over 3, right? Hence, non-convex on R, right? Okay, now we established that our two functions are not convex. Now, let's add them up, right? So f plus g of x is equal to, well, we're gonna add this guy, and then this guy is gonna cancel. We're gonna be left with this guy, right? This is the whole point of defining the functions this way. So this is equal to alpha x squared, right? We can say let h equals f plus g, so we don't have to write it again. So h prime prime, we want to show that this guy is convex. H prime prime of x is equal to 2 alpha, right? Is this convex? Well, here in the question, we know alpha is bigger than or equal to 0. So this guy is going to be greater than or equal to 0. So we're good. This is convex. Is this alpha strongly convex? So when we have two cases, alpha is equal to 0, then this implies h prime prime of x is equal to 0 always. So this is convex, but this is not actually. Yeah, it is strongly convex because alpha would be 0 here as well. Yeah, so I was gonna say the second case where alpha is bigger than 0, 2 alpha is bigger than alpha, so it would be strongly convex. Um, yeah, I don't know if there's an equality here to be alpha strongly convex. If there is, then this is alpha strongly convex everywhere. If there isn't an equality here, then we'd have to do two cases. When alpha is 0, this is just convex, and when alpha is bigger than 0, it's strong alpha strongly convex. But yeah, this is the last question of the exercise. It was a proof. So as good proof writers, we're going to put the square here to indicate we're done with the proof.